All right, onward. We're on to lecture 23, part C. All right, now in this part, we're going to learn a little different relationship. So in the last part, we talked about, well, what happens when you change the pressure to the size of a gas? So that relationship was P1 times V1 equals P2 times V2. That relationship was called Boyle's law. Now in this part, we're going to talk about, well, what happens to a gas when you change the temperature? If you change the temperature, if the temperature goes up, does gas get bigger or smaller? How does that work? Well, similar to what I did last time, we're going to start with a little demonstration video, and then we're going to do some examples. So there'll be a little equation that goes with this. We're going to get into that in this section. All right, so let's start off with the demonstration video. Let me flip over to that. All right, so let me show you a little video where we're going to take a sample of a gas. So again, it's going to be a balloon. It could be any sample of a gas, but it's going to be a balloon. And we're going to change the temperature. And the way we're going to change the temperature in this video is we're going to put the balloons in liquid nitrogen. Now, liquid nitrogen actually has a temperature of negative, not positive, negative 197 Celsius. So it's super cold, all right? And what we're going to try to figure out is, well, when you get a gas really cold, what happens to the size of it? Does the gas get bigger or smaller? So let's go ahead and we'll watch this video and see what happens. All right, so let me go ahead and turn it on here. All right, so you can see they're actually pouring the liquid nitrogen in a bowl. So it gives off a lot of like fumes here because it's kind of evaporating as they add it. It's so cold. And after they add it, they are going to start putting in some balloons. All right, so let's watch it. All right, here goes in the first balloon. Now, at first, it's a little hard to see what's happening because you actually got to get them submerged to see anything. So they're going to push them down, and when they push them down, you can see the balloons. Oh, the balloons are in something super cold. They get smaller. So this idea that when you cool down a gas, it becomes smaller, that's also a law. That's called Charles's law. So let me go ahead and write that up here. Charles's law. It says that when you get a gas colder, it's going to get smaller. So let's write that down, okay? Let me pause it for a minute. Man, they're adding a lot of balloons in this clip. All right, so let me pause it for a sec, and we'll write that down. So Charles's law says that if temperature, well, decreases, like with these balloons being in that super cold liquid nitrogen, volume decreases. All right, let's keep on going with our video. Let's see what they do next. All right, so let's see here. They're cooling them down. And as they cool down, they're getting smaller and smaller and smaller. Man, they add a lot of balloons. All right. Maybe I should fast forward just a little bit. All right, I found this clip on YouTube. All right, man, they keep getting them balloons in. All right, I want to show you the next part then. All right, now what they do is they take them out. Now when they take them out, they're warming back up. They're getting back to room temperature. And as they warm back up, the balloons get larger. They're getting bigger again. Oh, let's write that down. So right now, the temperature is going up. If the temperature increases, these balloons, these gases, the volume of them also increases. So in math lingo, there's a word for this. They're called directly related. They're directly related. Now, that's all good to know, but if we want to do any math with this, we got to have an equation. And Charles's law is that equation. So let me go ahead and write it down. So Charles's law, oh, maybe I'll put it over here. He figured out V1 over T1 equals V2 over T2. So, oh, you can still see those balloons getting bigger, can't you? All right. So they're warming back up there. All right, so what's this mean again? Well, the ones are like your initial conditions. So that'll be like our initial volume and our initial temperature. The twos are going to be our, oh, I think I'm going to pause this here, our final conditions are final volume and temperature. Now, the only other thing I want to tell you about that's a little tricky is that the temperature can't be in any unit. For this law to work, these temperatures, the temps must be in Kelvin. If it's not in Kelvin, it's not going to work. Now, Kelvin, you might remember, is a unit of temperature. It's related to Celsius. It is, to be exact here, it is, let's see, how does that work? Kelvin is Celsius plus 273. All right, so we'll practice using this equation in just a minute. How do temperature and volume relate? V1 over T1 equals V2 over T2. That's going to tell us what happens when you change the temperature of something, of some gas. The only tricky thing, make sure those temperatures are in Kelvin. All right, with that, let's do an example. All right, let's do a little example using Boyle's law. All right, Boyle's law again, let me just write it back up. If you change the volume, if you change the temperature, what happens to the volume? Oh, I guess you could write it either way, actually, or say it either way, couldn't you? All right, this equation. Just remember, temp must be in Kelvin. All right, so let's do a little example. All right, a balloon, this one is actually based on that demonstration you just saw, okay? So let's say that balloon that they put in the liquid nitrogen, let's say this balloon, the balloon was initially had a volume of 1.8 liters at room temperature. So room temperature, like the temperature in your house right now, if we're thinking in terms of Celsius, it's probably about 21 Celsius. So a balloon has a volume of 1.8 liters at 21 Celsius. Now, just like you saw in that video, let's say the balloon is placed in liquid nitrogen, which is really cold, negative 197 Celsius. What will be the new volume? All right, so let's go ahead and we're going to have to work this out. What is the volume going to change to? All right, so if you're going to do this math, kind of like in the last equation, you basically got to know all the numbers except for one you're missing. So let's see where they're going to go. All right, so a balloon has a volume of 1.8 liters. That is going to be my V1. 1.8 liters. All right, at 21 Celsius. Now, 21 Celsius, that is my beginning temperature, but remember, you can't put it in Celsius. So before I plug that in for T1, I've got to convert it to Kelvin. Oh, how do you do that again? You take 21 and you add 273. So on the Kelvin scale, this balloon is starting off at 294. That will be my T1. Now, on the right-hand side, that's where you always put your new conditions. If the balloon is placed in liquid nitrogen, which is negative 197 Celsius, all right, so that's going to be my new temperature. So again, make sure you put it into Kelvin. How? You add 273 again. All right, so we'll take that temperature and add 273. And when you add 273, make sure you realize there's a negative sign there. You actually get 77 Kelvin. So if the balloon is placed in liquid nitrogen, which is negative 197, oh, that is my new temperature, 77 Kelvin. What's the new volume? I'm solving for V2. All right, so sometimes people get a little mixed up on what number goes where. Hopefully that makes sense. Now, once you do that, it's basically algebra time. Oh my God, what are we going to do? Well, we got to solve for V2. Now, this came up in a previous topic where we talked about fractions, or we did an equation that had some fraction looking thing in it. And I said, whenever you have a fraction, the best thing you can do is get rid of that. And the way you can get rid of a fraction looking thing, the thing I would do to start is cross multiply. That is not necessarily going to be the last thing we got to do, but it's a good first start because it gets rid of that fraction, and fractions are never your friend. They are never your friend. All right, so let's go ahead and do that. So what I mean by cross multiplying is we'll bring the 77 over to the left side. And then on the right-hand side, we're going to have V2, and we're going to bring the 294 over to the right-hand side. So now this is what I would have after I cross multiplied. Now we're not done, but we're kind of close to done. So, oh, let me ask you a question at this point. What are you going to do to get V2? If you've done this, there's still one more step, but you can get V2. Oh, you're going to divide by 294. Now, why are you going to do that? Because the 294 will cancel out, and then you'll be left with V2 all alone. You'll have my new volume equals this, 1.8 times 77 divided by 294. It should be like that. All right, so you'd have to type this in your calculator. Let me just tell you, if you type it in correctly in your calculator and you round and all that, my new volume would be, I got 0.47. Oh, got to have units on that thing. Let's see how that's going to work out. Kelvin and Kelvin. Goodbye, Kelvin. We're left with liters. That sounds great because we're finding a volume. It should be in liters. All right, so we rounded, we wrote units. Don't forget all those little things that are important to me. All right, important to chemists in general. All right, last thing, like we did in the last section. Does it make sense? Well, the temperature went down, right? We stuck this balloon in liquid nitrogen. The volume should be going down. It did. It went from 1.8 to, well, 0.47. So it went down. All right. Let's try another one. Let's try another one. Oh, I hope this is making sense. Let's double check, though. Let's try one more. All right, let's flip over and we'll do one more. All right, one more example of using Boyle's law. All right, one more example. All right, Boyle's law has to do with when you're changing the temperature. All right, so let's see what this question says. A balloon has a volume of 2.5 liters at 21 Celsius. So again, that would be like in a room. Rooms are like 21 Celsius. A balloon has a volume of 2.0 liters at 21 Celsius. If the balloon's taken outside and it expands to 2.35 liters, what's the temperature outside? What's the temperature outside? All right, we're going to work it out in a minute. Before we do that, let me just ask you a question. Look at those numbers. Is it colder outside or is it warmer outside? Think about it. Oh, it should be warmer outside. Look at the volumes. This balloon is getting bigger. If its balloon is getting bigger, that's because it's hotter outside. So when we solve, we should be getting an answer more than 21. It's hotter outside. All right, let's actually figure it out. So we're changing the temperature. Boyle's law is going to help us. All right. The other thing, we got to put in the numbers and make sure you remember temperatures have to be in Kelvin. All right, let's work it out. A balloon has a volume of 2.0 liters. That is my beginning volume, 2.20 liters. At 21 Celsius. 21, that's going to be my beginning temperature. You got to convert it to Kelvin, though. So you add 273, it's 294 on the Kelvin scale. That is my T1. If the balloon is taken outside, it expands to 2.35 liters. 2.35 liters. Oh, liters. Oh, that's got to be a volume. That's got to be my new volume. 2.35 liters. What's the temperature outside? So we're going to solve for T2 this time. All right. Let me ask you another question. I think we got everything in the right place, don't we? I hope. I think we do. All right. Next question. How do you do the math? What is your first step? What's your first step going to be? It should be cross multiplying. And what do you get when you do that? Oh, I'll write it out. You get 2.20 liters times T2 equals 2.35 liters times 294. All right. We cross multiplied. We ain't done yet, are we? So let me ask you the next question. What's the next step? What are you going to do next to solve for T2? Oh, it's divide by 2.2. So you'll divide by 2.2 liters. Why? Because we got to get those 2.2 liters to cancel out. That's why. You got to get T2 all alone, right? That's the goal. So that's the way we're going to get it done. All right, so now I think we got the answer. T2 would equal this. All right. If you're working on your calculator, you multiply, you divide, and all that. You type that in. Oh, let me check my notes here. I got 314. And is that what I got? Yeah, 314. Now, just to be careful of the units on that, liters, goodbye, 314 Kelvin. It would be 314 Kelvin outside. Now, if I wanted to know the temperature outside in Celsius, I didn't really say that in the question, but if I did, to get from Kelvin back to Celsius, you don't add 273, you would subtract 273. So on the Celsius scale, I should say, works out to be about 41. 41 is hot. That's like a little over 100. So it would be pretty darn hot out on this particular day. All right, so hopefully this is making sense. If I'm going over a little fast or a little worried about the algebra, you can always like rewind and watch this again. That's the only one I'm going to do on this topic, or the only two, I guess. So I do have one more thing to tell you in this video, not so much mathematical, but one more idea I want to go over. If you're struggling or a little unsure of the math, yeah, just watch it again. And again, Zoom, maybe we'll talk about this a bit more then. All right, so let's get to our last little bit of this video in the meantime, though. All right, so the last thing I want to bring up in this lecture is kind of a way that we kind of imagine the way gases look, like if we could see the particles. So there's no math in this last little thing. It's more like, you know, if we could see what's going on inside of a gas, what would we see? And what we would see, or the idea behind this, is something called the kinetic molecular theory. It's sort of a way of thinking like what's going on inside of a gas. So first part of this theory is that gas particles are just a collection of particles that are in constant motion. So inside of a gas, you have little particles, maybe oxygen or nitrogen or argon, some other gas. It could be anything really. And these gas particles are always moving around. They're always moving around. All right, so they're in constant motion. Now, the other thing I'll tell you about this actually is the reason why we get pressure. It leads to pressure. Leads to pressure. How does it lead to pressure? It leads to pressure because these particles, they're going to strike the like sides of the balloon or the sides of some container, whatever container they're in. And when they hit the sides, that's what pressure is, their force as they run into the sides. So it leads to pressure, we'll say, as they hit the sides of the, oh, let me fit in here, container. All right, what else do we know about gases? Inside of a gas, there's no attractive forces or repulsive forces between particles. All right, so gas particles, they're not particularly going to try to get closer to each other. They don't particularly like each other. They don't particularly like to spread out either. So there's no attractive or repulsive forces, all right? So won't have to worry about that. What else do we imagine about a gas if we can see it? There's a lot of space in between the particles compared to the size of the particles themselves. So what does that mean? Well, you kind of see that in this diagram. The actual little particle, oxygen or nitrogen or whatever it is, it's pretty small. And then there's these big gaps till you get to the next particle. So it turns out in a solid and a liquid, that's not true. In a solid and a liquid, the particles are really close to each other. But in a gas, there's a lot of empty room. There's a lot of empty space. Now, that also kind of affects something we've been talking about, which is gases can change size. And they can change size a whole lot. You can take a gas and you can make it way smaller by like cooling it down, for example. So because there's all this room, the particles can get closer together or they can get even more spread out. depending on what we do. What do we do to the temperature? What do we do to the pressure? So, how should I say that? I guess we'll say it makes them compressible. They can change size kind of drastically. Um, Liquids and gases don't tend to do that. Last thing, the speed the particles move increases with increase in temperature. So inside of a gas that's hot, they're moving faster. Inside of a gas that's cold, they're moving slower. So they're still moving, but way slower. All right, so that's called the kinetic molecular theory. All right, that's pretty much it for this lecture. Let me just tell you, there is one more gas law that we're going to talk about, but I'm going to talk about it in our Zoom time because I feel like, gosh, it's been about an hour, and I'm trying to keep these things to about an hour. So one more gas law that'll come up during our Zoom session, and you'll see it on your homework. We'll talk about the combined gas law. So yeah, there's more equations to be familiar with, more math to understand. We'll get to the combined gas law, but oh God, I think that's enough for now. Let's do it in our Zoom time. All right, so with that, if any of this doesn't make sense, let me know. I'll try to help you out. Otherwise, I'll see you on the old internet pretty soon. Hope you're doing good. See you next time.